Welcome, everybody. Let me start a little bit with some motivation. So there's a project we just started. It's called the Hearables Project. And it was kind of inspired by this funny device that the Star Trek people used to wear back then. The idea is that we want to have a system that can basically curate your listening environment. So you have this thing in your ear. It can detect things that you want, things you don't want, and it can basically react appropriately. And of course, we want this thing to work in real time and inside your ear, which has an interesting hardware component as well. So you've probably seen stuff like that before. For example, there's an obvious list of things you might want to do in those cases. Maybe you want to lower the sound intensity when it gets too loud, or maybe you want to EQ whatever the sound that you're listening at so it fits your hearing style or suits your ears. And you can also have those things, of course, do a lot of listening on their own. They can, for example, measure your heartbeat and do stuff like that. And that's kind of like the usual stuff that pretty much every company wants to do. The stuff that we're focusing on is a little different. What we want to do is we really want to change and remix the audio that comes into your ear through that device. So, for example, if I'm watching a TV downstairs in my living room and my baby is crying upstairs, I want that sound to be boosted so I can hear it, but I don't want to hear the baby crying next door. So you need to have an intelligent system that actually understands what sound is what and then how to just boost that sound. We want to be able to do things like virtualize audio. Maybe I don't like the reverb in this auditorium and I want to listen to my voice with a couple of semitones lower. We want to do all this kind of augmentations and sound. And we also want to be able to sort of group a lot of those hearables together. If everybody in this room had that device, we should be able to get an amazing sound quality out of it. How do we, what are the algorithms for that? So these are some of the things that we're working on. And just to give you some examples of what we mean, so here's a couple of cases. Forget the video part because that was part of a bigger project, but focus on the audio scene. So let me just play this audio, this video first. So there's a bunch of stuff happening. Not really. Oh, come on. There we go. Now, there's a bunch of stuff that happened in the audio space there, right? I mean, how many sounds did you guys hear? Any takers? There was the AC, right, which is pretty annoying. There was Irene's voice, Kevin's voice, and then the music playing from the laptop. Now, what we did in there is we went in and said, you know what, there are certain things we don't want to have in that video. Let's try to remix it. And this is what we got as an output. Damn it. So forget the visual part because that was part of a bigger thing. But what happened here is that we removed the AC voice and we removed Irene and her voice. At the same time, the music was playing all the time and Kevin's voice was unchanged. A slightly different application. Here's an example where we manipulate music. So here's the input. And in this case, what we want to do is make a good piece sound worse by changing the melody. And we have a system that can basically transform into something that sounds like this, where the melody is different. And sort of the core functionality there is that we're able to basically understand that there are multiple sounds in there, only some of them need to be processed, and we have to have this general awareness of what's going on in the auditory scene before we can start remixing it and doing whatever it is we want. Now, we do have the algorithms for that. That's not that big of a deal. The big deal is that we want this thing to run in real time, and we want it to be running in somebody's ear without burning their ear canal because it consumes too much power. So we have to be somewhat creative with our use of algorithms. Otherwise, a project like this would never fly. So what am I going to talk about in this talk? I'll talk about basically compressing all of the work that I've shown into one common computational core, which, surprise, it's going to be a deep learning pipeline. And then I'll talk about two things. One of it is how do we get the system to run efficiently enough so we can have it in hardware that can fit in the constraints that we have. And then part two is how do we change the way that we do learning in those situations to facilitate that hearables model, where you will have to learn things on the fly, where you will never necessarily get clean data and sort of have to do things in the wild. So just to talk a little bit about the sort of computational core, those of you that work with raw audio probably know that by nowadays, everything you want to do should be done or could be done with a neural network. I'm not a big fan necessarily, but you can solve a lot of problems really well that way. And the general process is what you do is that you get a bunch of input sounds, then you get what the output should look like, and you basically learn a regression system that does that. And most of the time, it ends up working really well. Again, if you look at the sort of acceptance from the crowd, what I'm showing here is the top 10 or 11 words from titles from the ICASP submissions in the audio and acoustics track. One thing you might notice is that, yes, there's sort of speech and music, which are common words that gives you the domain that people are working on. There's some pointless work like words like sound, audio, and acoustic because, people felt they have to put those things in there. But if you look at the red bars, they correspond to a neural deep and network. And these are the second, sixth, and whatever, 10th most popular words in titles. So most of the papers submitted in that track had to do with neural deep learning, even more so that they had to deal with specific problems. So what is the pipeline that people use there? If you look at a standard audio processing pipeline, it usually looks like this. You have a sound that for some reason you don't like because it's noisy or it's got artifacts or whatever. You put it through some kind of a filter bank and then subsample. Most of the times that ends up being the STFT. Then you do your processing. And then if you want to get an audio output again, what you do is you upsample, put through the inverse filter bank, and out comes your sound, right? So any standard, the reverberation, the clipping, enhancement operations usually follow this kind of a pipeline. Now, the way that this has been reinterpreted nowadays is a neural network, where now we're going to say that, well, instead of having a filter bank like the Fourier transform, we're just going to have a convolutional network. And if you put the Fourier basis in there, it will be a Fourier transform. If not, it's going to be something else that we can learn. There's some sort of max pooling or stride operation that does the subsampling. Then you have this neural network that takes care of what you want to do in that new latent space. And then you have sort of the upsampling and a transpose a convolution that takes you back to your original space. If I were to take a neural network like this and put inside it the stuff that we use in a DSP pipeline, it would be identical. But the magic here is that I can say these are all learned parameters, and I can learn them optimally for my problem if I have good enough training data. So that's what most people are doing. Just to give you a sense of how this thing works, for example, in a simple problem like denoising, let's say that we take a simple sound like this one here. So that's speech and a phone ringing. I'm sure none of you has heard this sentence before, right? So again, if we have a spectrogram, we can clearly see that there are some regions where we have this ringing phone. A silly thing we might want to do is say, well, what if we just zero those regions, right? And if you do that, you get something that doesn't sound great, but it does the job.
She had your dark suit in greasy washwater all year.
But of course, that's not what I would advocate you would do. The right way to do it, at least as far as the textbook goes, is you would have to learn the optimal filter. So how do you do that? Well, you find something about the spectrum of your desired source. You try to find something about the spectrum of your desired of the noise that you expect. You can come up with an optimal linear filter. That's when you apply that on the spectrogram, you can actually get the best possible denoising performance. And I'm writing this in a funny way. That's basically a linear filter. But the way that I'm going to write it is that I'm going to have a matrix that's going to be my spectrogram. It's going to have frequencies times time. I'm going to multiply that by a diagonal matrix that has in its elements the coefficients of my filter. So effectively, I'm multiplying every frequency track with a coefficient, just applying the filter, and that will produce the output that I want, right? That's a standard way of doing that. I'm writing it that way because we're going to expand on that. How does that sound like? Well, it sounds a lot better. If it starts. Yeah, I noticed.
She had your dark suit in greasy washwater all year.
But we can still see that, there's some artifacts there, although you can't hear it very well. And now the magic comes from the realization that, well, what I've done here is I just applied a linear transformation on my input data. And the one thing that we've learned from the world of deep learning is that everything that's linear should become multi-layer and non-linear. So to get there, what do? Well, we just complicate things a little bit. We can start by our setup that we had before. That's a simple convolution in the frequency domain. And now what we're going to say is that, you know what, I'm going to take my data, I'm going to convolve it in the frequency domain with a full matrix this time, so it's a bit more complicated operation. I'm going to apply some nonlinearity, and then I'm going to keep doing that over and over and over. And what that buys me is that I'm adding a lot more parameters, and I can make a much more elaborate model. So by doing that, I'm effectively turning my simple linear filtering operation into a multi-layer network. Okay, so that's the standard thing that everybody's doing nowadays. And we can go all the way with that, and we can say, you know what, my inputs, that was my STFT data, doesn't have to be STFT data. What if I use another layer that has a bunch of filters that get convolved with my raw inputs, and then just find the optimal domain to do my processing? Because your Fourier transform is not necessarily optimal for what you might want to do. So if you put all of those things together, you can actually get some pretty good systems that can do a lot of very difficult problems and sort of solve them really well. Just expanding on this denoising example, just to give you a couple of cases here. So typically what you would do in this case is you wouldn't necessarily start with the power spectrum of your source and your noise, which is what we did with the optimal filtering. Instead, what you would do is you would take, for example, a lot of noisy signals, and you would take a corresponding clean signal for that, and you would effectively train your neural network to try to map every little segment of your noisy input sounds into a corresponding clean sound. If you can gather data like that, then that's, that gives you your training data set, and that's not very difficult to do, and effectively that's a noisy autoencoder. So it's a well-known sort of structure. It turns out that that's much better than anything else when it comes to doing source separation. You can get the state-of-the-art results right now are coming from those algorithms. And just to give you a sense of how powerful it can be, here's an example of a single-channel mixture. And this is what such a neural network can give you as an output.
We have no basis to believe it's done very.
So that's sort of insane performance. If I heard that 10 years ago, I would say there's no way this is even theoretically possible. But we have systems that actually do that quite easily. And if you look at the literature nowadays, this is not necessarily only limited to denoising. If you want to do the reverberation or declipping, auto-tuning, whatever, all of those problems can be solved with a pipeline like this. And of course, part of the beauty of neural networks is that you can come with a lot of architectures that incorporate new developments and sort of do fancier things. So you'll find a lot of papers where they use all sorts of different types of layers, convolutional, recurrent, or they use adversarial learning. You can extend this to multi-channel versions. And using these algorithms allows you to use an arbitrary cost function. So if you care about audio quality, you could use something like PESC. If you care about intelligibility, you could plug in an ASR system. You can do whatever you want to get a result that optimizes the one thing that you care about. So the key here is that this kind of a pipeline could be a nice core to do the kind of stuff that we want to do for our hearables. It means that we can use the same pipeline to do a whole bunch of tasks at the same time. So we don't have to worry about designing a reverberation algorithm and then a different classification algorithm and then a different denoising and so on and so forth. So that looks good on paper, and if you're an academic, you're happy at this point. But the problem is that we have to start worrying about computational efficiency. So the processing that I've shown so far is very, very demanding. We're not doing Fourier transforms anymore. We can't use efficient algorithms. We have a lot of big filters. We have a lot of matrix multiplications that happen in very high dimensions. And remember, I want those things to run in a hearing bud. There's no way you can have those things running in such a device easily. So the problem is that what we care to do is some sort of an edge computing. We want to have small devices to run those algorithms. And these devices are not going to have a GPU inside them. They're not going to be able to maybe do floating point even. The memory is going to be very low. And we have to have these things work in real time with low latency. So that creates an interesting problem for us to work. Now, the main problem that we have with those algorithms computationally is the fact that we're using floating points. If any of you do hardware, you know very well that the moment you start doing floating points, the size of your hardware explodes, the power goes up, and it becomes a very sort of a completely different setup from what we had before. So what we're going to do is we're going to take those algorithms and try to find a way of computationally expressing them in a much simpler form that will facilitate easier hardware. So how are we going to do that? Well, what we're going to do is we're going to go all out with quantizing. And yes, there's a lot of literature that shows how you can take your neural nets and compress them down to 8-bit fixed point or stuff like that. We're not going to use any of that because that still requires a lot of logic on chip. Instead, what we're going to do is we're going to binarize our network. That means that every parameter that we're going to use is going to be a single bit, either 0 or 1. Okay. The reason why we want to do that is because now the hardware can become a lot simpler, and it will give us a glimpse of hope for running this thing inside somebody's ear. So how do we get to that? What do we have to do to binarize a network? So let's look at a typical neural network unit and kind of get a sense of what it does. So typical old school type neural network unit would work like this. You would provide a vector x as an input. That gets dot producted with a vector w. That's going to be the parameter of that node. And then once you take that dot product, you put it through some kind of a saturating function, let's say hyperbolic tangent, and that produces your output. Okay, that's the computational core of a neural network. Now, if you think about what happens here, there's kind of like two situations. If you have a lot of agreement between the sign of my input x and its corresponding parameter w, that means that you're going to get a product that's going to be positive. And then if that happens a lot, that means that the summation is going to give you a big number, which means it's going to saturate. So if we have agreement where both the x and the w are, say, both positive a lot of the time, or they're both negative a lot of the time, you're going to get this function to saturate towards +1. And that means we have a lot of correlation or high agreement between the parameters and the inputs. If we have a disagreement between the signs, which means that when w is negative, x is positive, or vice versa, then you're going to get a small number, or a small negative number, or rather a large negative number. And that means you're going to saturate your hyperbolic tangent towards -1. So effectively what this neural net node is doing is that it gives you a sense of how much you tend to have agreement between your input signs and your parameter signs. So if you get a +1, it means you have a high agreement. If you get a -1, it means you have a low agreement. So now what we're going to do is we're going to take that operation and map it into a binary operation. So we're going to say, let's take our +1 and -1, and we're going to map them to 1 and 0. And now what we can do is we can replace that formula with a binary set of operations, where instead of multiplying my w and x, I will instead take the XNOR between my w and x, where now w and x are going to be just bits, right? They're not going to be real numbers. Now, why do I want to use the XNOR? Well, if you look at the XNOR table, what happens is if my parameters are both 1, I'm going to output a 1. If they're both 0, I'm going to output a 1. But if they differ, I'm going to output a 0. So now if I see that I do this kind of operation, and I see that, say, more than half of my bits are set, that means that on average, I get more agreement than disagreement on my inputs and my parameters, which would be the same thing as my x's and my w's having the same sign. If I see that less than half of those operations give me a 1, it means that I have a lot of disagreement. So instead of using this saturating function, which is a nice, gentle, differentiable function, instead what I'm going to do is I'm going to count how many bits are being set. If more than half bits are being set, I'm going to send out a 1 as an output. If less than half the bits are set, I'm going to send out a 0. Right? So that way I'm doing a very, very crude quantization of the operation of the real space. But now, all of the stuff that I'm doing here is this simple bitwise operation. Now, what does that mean when we try to compare our networks? For a real valued network, you would have, for example, a matrix being multiplied with a vector input. And then you would put that through some kind of a floating point function, and then you would get your outputs coming out. The equivalent to that would be that now all of the values in our matrix would be bits, as opposed to floating point or a fixed point representation. Instead of doing a multiply and accumulate, we're going to be doing an XNOR and a pop count. And then instead of applying some kind of a floating point function, we would basically have to see if that pop count is bigger than a threshold or not. And then the output, again, is going to be just bits. It's not going to be floating point numbers, and then we can use those for the next layer and keep going. Now, there's a couple of things to note here. If we want to train such a network, we still don't have a good algorithm that does that. So the training will still have to happen in real parameters, but the inference can happen in this binary space. There's a couple of things we have to change on the training itself. There's a bunch of algorithms that came out since we first did this, but the original approach was that we apply a saturating function on our parameters, and we have a regularizer that tries to maximize the L1 norm of our parameters. What that means is that as we're learning our parameters W, we try to make sure they're as big as possible, and that means they're going to start saturating a hyperbolic tangent, which means that ultimately what we'll be multiplying in here is either a +1 or a -1. So by doing that, we're forcing the network to find a binary solution. And if you do that, it actually works pretty well. There's one more trick that we have to worry about, and that is that we have to use appropriate inputs. We cannot use real valued inputs for the system because it's expecting to find bit representations. So we would have to either find a way of quantizing our data or use some kind of a fixed point multi-bit representation or maybe a binary hash. And once we have that way of manipulating our data, we can put it through our network, and it can actually do what we want. Now, that's, of course, a lot of fuss and a lot of effort. Why is it worth it? Well, let's take a look at the comparison between a floating point and a real and a bitwise network. If you only look at one connection for a neural network, you would effectively have to do something like a 32-bit real multiplication, right? Which is not a simple circuit. It's not complicated, but it's not trivial. The equivalent circuit for that would just be an XNOR gate, right? So huge reduction. If you look at one node, you're probably going to have 1,000 nodes feeding into one node. That means you're going to have about 1,000 of those floating point units doing a multiplication, whereas in our case, we only have to have 1,000 of those XNOR gates, and then some mechanism of doing the population count of those. If you go to one layer, then you start getting into the megaflop territory in 4 megabytes, whereas for a binary network, it's 2 megabit ops and 0.1 megabytes, so a huge reduction in the amount of data needed. And for a full network, you're actually going from a fairly big model, a 16 megabyte model, to something that's less than half a megabyte in binary space, if you're using the same number of parameters. Now, these are the numbers that get me most excited. We actually did the the early hardware design for that, and what we found out is that if you had, for example, an area, if you look at the area for an implementation for a 32-bit float neural network, it's going to be about 6,000 microsquared meters. If you do it for 6-point quantization, that goes down to 1,000. If you do the binary network, you go down to 100. So we're getting 2 orders of magnitude improvement on the area needed to do this kind of hardware implementation. And if you look at the power, same story, we get about 2 orders of magnitude improvement in the amount of watts that we require to run this thing. So now that gives us hope that we can actually stick this into somebody's ear, and it's going to be okay, it's going to run, and it's not going to kill the battery or overheat. So now the question is, okay, that's nice, but does it work? Well, here's a simple case. Again, going back to the denoising problem, we could easily take something like a spectrogram representation of our sound coming in. What we do in our case is we quantize this to a 4-bit representation, so we provide an input vector that's 4 times bigger than the original dimension of our data, but we're just sending in the bits as they are. And then if you look at the results that we get out, here's a specific denoising example. What you're seeing here are metrics, the SDR, signal to distortion ratio, signal to interference, and signal to artifacts. The higher they are, the better. The dark blue bars show the performance that we got using a real valued network. The light blue bars show us the performance that we get using a binary network that had exactly the same number of nodes. So now that means we're going to have 32 times less memory requirements, right? Because we have a much smaller network. And what you'll notice is that, yeah, on average, we're getting about 1 dB less performance, but it's still hanging in there pretty high. If you use a network that has a bigger size, in this case, we have 2048 nodes in 2 layers. Again, the performance doesn't end up being as big. So if you're willing to get a drop of 1 dB performance, you're getting 2 orders of magnitude more computational efficiency.
So when you're doing these experiments for the light blue bar, right, you're going to train the network using that the other formula you showed me where the branch was inside
Yes.
the sum. And then when you're done, you're going to quantize the whole thing.
Yes.
Right? Do you consider training the other way where you have a mirror image or a copy of the network which is already binarized and do the back propagation based on the output of the binarized network? In other words, don't worry about what the original network puts out.
Yes. So what happens is that
quantization might be good enough that you don't need to back propagate anything.
Yeah. So what we do is kind of similar in practice, because once you train that real valued network, what we do is we move it to a mode where the forward pass is real valued, but the backward pass is using the quantized values. Sorry, the forward pass is quantized, but the backward pass is using real values, which is equivalent to what you said. But that ends up being a fine-tuning stage just to make the network understand that there's some quantization noise that it didn't deal with before. But the bulk of the processing just happens in just plain real values. Since we did that, there's a bunch of other papers that sort of have different ways of training this. So in fact, most people don't use the hyperbolic tangent on the weights anymore. They just hope they're going to end up being big numbers, and most of the time they do. So there's like lots of voodoo that that gets in there. Okay, so any questions? Any other questions? Okay. So what's coming up next after that? Well, we're also looking at hybrid models where maybe some of the layers could use some kind of an integer or floating point arithmetic. It can buy you some performance. So we're exploring, what is the sweet point of using, both types, and what can give us the performance characteristic we want. We're sort of extending this to all sorts of other architectures. So we already have a binary ResNet and a WaveNet. And we're also very much interested in looking at binary transformations. What if you replace the Fourier transform with some kind of a binary transform? How do you do processing in that space? What does it mean? And it's going to be, of course, a lot very efficient. So that's something that we really want to do. And then the sort of final thing we were thinking about is that we should go all in. And instead of using some kind of a PCM representation for a waveform where every sample value is some kind of a fixed point number, we could perform data on PDM streams. Everybody know what PDM streams are? Only the old-timers? So PDM stream is a pulse density modulation. That means that your sampling rate is much, much higher. And by how many times you fire within an interval indicates how loud your waveform will be. And what's nice with this representation is that it's completely binary. If you have a MEMS microphone today, they usually give you the signal in that form. So that ends up being a very interesting stream to work in. And there's practically zero work on how to do DSP in that domain, which is kind of fun. Yeah.
A question. Sigmoid or softmax, still we can use this kind of binary. My kind of question is, recently people are more kind of how to say, using, for example, sigmoid, we can make a gating.
Yep.
And then we can, for example, extend it to the LSTM or whatever.
Yes.
And the softmax, we can actually use it for the attention. And then a lot of kind of attention-based new advanced architecture can be also applied. So I'm very curious whether this kind of a binary concept can be applied to such kind of the first sigmoid softmax and then the LSTM or attention-based.
Yeah. So Minja Kim, who was the student of mine that worked on that, actually has some papers using LSTMs, which are binarized. He did it after he graduated, so I'm not that familiar with that work. And the softmax, I think I've seen some papers that do an equivalent of a softmax in there too, but I don't have a reference.
Yeah, very interesting because then it can kind of have forcing the sparsity of the attention if it works like a binary. So
yeah.
It's maybe a kind of good kind of property actually. So not only for the approximation, but okay. Thank you.
Yeah, it's still early days for binary networks, so we're still figuring things out.
Very cool.
All right. So at that point, we're sort of somewhat happy that we have a computational core that we can use, and then we have to turn our attention to other stuff, which has to do with data. So now the problem is that with a lot of neural nets, you need to have a good training data set. Otherwise, things don't really work very well. And trying to build those sets can be quite time-consuming. It's also something that's always subject to some bias, right? If you collect a lot of faces for face recognition. Invariably, you're going to forget to include certain races, right? It's a well-known problem. So we really want to avoid having some of that too. But more importantly, the sort of hearables model that I'm trying to present here is fundamentally incompatible with this kind of processing. Because whenever you want to have, for example, my hearables, and I want to instruct them and say, you know what, that sound over there, I don't like it, stop it, I'm not going to have training data set for it. It's going to have to learn in the wild. So we're going to have to find ways of dealing with training where we don't have to use this kind of getting a data set up. So let me fall back to sort of how we traditionally train things and then see how we could improve that. So if you want to have a network whose job is, for example, to do some kind of enhancement or denoising, usually what you would do is the following. You would get a whole bunch of clean speech sounds. And this would be your ground truth as an output. And then you would get a whole bunch of noises. You would artificially mix the noises with the clean sounds. And you would provide those as the inputs. And then for every input, you know exactly what the proper output should look like. Once you have that set up, it's very easy to learn a neural network that basically maps the inputs to the output. So it becomes very standard. Now, as you might notice, this is a little bit problematic, right? Because that means is that I cannot use real-life mixtures because I don't have the ground truth for mixtures. I have to use synthetic mixtures. So what are the problems here? Well, if I use synthetic mixtures, I will introduce some bias into the system. I'm not going to learn from real data, and I'm probably going to be using some kind of a simplified model. It's a well-known effect that people design these amazing neural networks that do amazing denoising work. The moment you deploy them inside a room that has reverbs, they fail miserably. Why? Well, the data doesn't reflect that. So the question now becomes, how can I make a system learn to do tasks without having to basically provide it such a carefully curated data set? And the sort of inspiration we're going to find from there, we're going to try to go from, is to sort of try to think of the way that we learn how to do things as humans, right? So if you've ever done any kind of audio processing, usually what happens is people say, you know what, we have these recordings, and I don't know, they sound like this, but we want them to sound like that. And nobody gives you an exact mapping from an input to an output. Instead, you're being given examples of, you know, here's some reverberant recordings, here's some clean recordings. You see what I'm trying to do here, right? That's how we sort of teach humans. So that becomes a much easier data collection task because it's much easier for me to get a whole bunch of, say, reverberant sounds or noisy sounds and a bunch of nice sounding sounds because I don't have to worry about having a ground truth for every input that I have. So what we want to do now is basically use this kind of a setup where I can get a lot of real-world recordings that exemplify what the inputs and the output should look like, but I don't have a mapping between the two of them. So the approach we want to use for that is equivalent to the style transfer. So this has been a very popular thing in the imaging space. You've probably seen some of that work. So what people do in graphics and computer vision is they have these style transfer networks where they say, well, I have one picture that looks like this. I have another picture that looks like the Great Wave. Can you try to render this picture in the style of the other one? And they have all these nice algorithms that basically take that picture and sort of redo it in the style of another picture. So if you want your portrait in the style of Van Gogh or something, you can get that done very easy. And in some sense, this is kind of what we want, right? We want to say, well, we have some sounds that sound like this. We have some other ones that sound in a different way. Can you transfer the style of the second type into the first one? Where the second style could be the dereverberated sound or the clean sounds or whatever. So how do we design an audio transfer net? Well, it actually ends up being relatively straightforward. We're going to use two sets of training data. So for example, let's say we want to do denoising. I'm going to get a whole bunch of clean speech recordings, and these are going to be, one style, the style that I want to have as an output. And then I'm going to get a whole bunch of noisy speech recordings. It could be different people, different environments. It really doesn't matter, as long as they exemplify what it means to be noisy and what it means to be clean. And then what we're going to do is basically have a two-stage training process, or sort of a two-objective training process. One of them is that we're going to train two autoencoders for every style. We're going to train a clean sound autoencoder and, say, a noisy style autoencoder. And these are basically systems that you give them the input, and then they have to basically represent the same thing as an output on the other end. But additionally, what we're going to do is we're going to add what we call cycle passes. I'm going to explain that on the next slide. And the whole point of the cycle passes is to make sure that for a given sound, you use the same representation if you see it as a noisy sound or a clean sound. So what does that mean? Well, let's look at what the training process will look like in steps. So the first step is we're going to train two encoders which work separately, right? So I have my style A, which is going to be, for example, let's say clean speech. I'm going to learn some kind of an encoder. It's going to have a latent representation, which then will be fed into a decoder, and that should be able to reconstruct the input exactly. And then I'm going to do exactly the same thing with a different encoder and decoder for the style B. That could be my reverberant audio or whatever. On top of it, I'm going to add what we call the cycle paths. So what are these going to be like? The first one is we're going to make a path that takes style A, let's say it's a good clean audio, maps it into non-clean audio, and then maps that back again into clean audio. So that looks like a path like this. So I'm going to take, for example, a clean speech. I'm going to put it through my clean speech encoder. I'm going to get a latent space for that. But then I'm going to feed that into the noisy speech decoder. And that will generate some kind of a noisy speech coming out of it. I'm going to take that. I'm going to put it into the noisy speech encoder. I'm going to get a latent space, and then I'm going to take that out to the clean speech decoder. And my goal is to get the same output coming out of here. What that means is that both the decoder and the encoder have to be able to deal with the same type of signal. And it means that if I take my sound and reimagine it as a noisy sound, I should be able to find a way of inverting it and bringing it back to my original domain. So I'm creating the ground truth by making this path. And I'm going to do the same thing the other way around, where now I'm going to take my noisy audio, I'm going to put it through its encoder, try to render it as clean audio, feed it back in the clean audio encoder, and then try to reinterpret that as a noisy audio again. And the only catch in there is that I'm going to add a constraint that whenever I do that, I'm going to have to use a shared latent space, which means that I'm going to have to use the same representation for my sound with the clean sound that's coming in and its reimagined noisy version as it gets denoised. If you prefer math to pictures, here's what happens. We essentially have four kinds of losses we're optimizing. The first one is we're trying to make sure that the autoencoder for style A does a good job at replicating style A, likewise for style B. And then whenever we try to reimagine the style A put through both the decoders, we also want to make sure that our two latent representations look the same, and likewise for the other path, we'll get the same thing again. So the end result is that the encoders and decoders become really good at understanding and rendering the two styles of audio that we want to use. But because we're using a common representation in the middle, it means we can anytime swap the decoder and basically render the same sound as a different style. So if you had, for example, a denoising setup, you could say, well, here's a clean recording of somebody saying, hello, it's me. That will be encoded in some spot in our latent space, and that will end up being roughly the same spot that you would get if you were to put in a noisy recording of somebody saying, hello, it's me. Now, whichever of these two you put, you're going to end up in the same latent space, which means that then you can render that particular utterance either in the clean style or the noisy style, or reverberant or whatever. Yeah. So there's no parameter sharing. The only sharing is on the latent space.
So encoder to how to say transfer to the kind of encoder is for say clean speech, and then transfer to the noisy speech.
Yep.
I could kind of understand that transformation, but how to say it may not be kind of a one-to-one. I mean, for example,
yes.
Clean speech with fun noise becomes fun the noisy speech.
Yes. There's multiple noises that can map to the same point for that particular utterance. Yes.
Yeah, that's my question. But do you actually how to say what kind of sound is generated? Just we don't have such kind of pattern. Just go through after you trained it. What kind of a noise? I think it's as a cycle. It's actually after that you will also have a denoising stage.
Yes.
So it can be okay. But I'm very curious. So what kind of arbitrary noise is kind of injected in the intermediate because it doesn't have a solution?
Absolutely. So you're at the whims of your neural net in this case. There's no ground truth. The only thing you're doing is reimagining or hallucinating an output the way that the data suggests. But we're not optimizing a cost function that tells you I'm going to get, this kind of an output coming out.
Right.
So there's no, no analysis we can do at that point. There are cases where you can have a variational component in here, so you can see the random number to help you, sort of change the variation of the outputs. But it's as with typical neural networks, sort of accept what you get. And,
sure. But we could you listen some of the audio after the transform?
I can.
Clean to noisy.
Yeah, let me show you some examples. I have some in the next slide.
I have one more question which is I think related to this one. So if I look at the purple boxes alone, they're like an autoencoder.
Yep.
And they are able to regenerate, resynthesize noisy inputs and noisy outputs for genuinely noisy ones.
Yeah.
Do they also have to be good autoencoders for the fake noisy things that you produce by going down this path?
Yes, because they're trained on that as well.
So they're trained on both.
Yeah, because if you look at that, well, so the path that's being taken is that I will take a clean utterance, render it as a noisy one, and then feed it back in.
Right.
Oh, actually, no, you're right.
It doesn't get that
well, because I'm using the same latent space, in effect, it's influencing that
latent space from having one region to model the real noise, another one to model the
I see. I'm not explicitly saying that, but because there's a sharing of the latent space, I think the decoder will have to adjust to that.
Because what Funny back there was asking me was something related to something you've done, where he uses a GAN to say that the fake noise has to match that of the real noise.
Yeah. All right. So what is the advantage of this? Well, we don't need to have matching pairs of inputs and outputs, which is a big win because oftentimes you don't get that. It can apply to a whole bunch of mappings and sort of focused on the noisy, on the denoising case, but you can do this for a whole bunch of things. I have some examples here too. And what's nice about it is that it also allows for incremental task learning. That means that I can learn my autoencoder for clean speech, and that's never going to change. But now maybe I go in an environment where I get a different type of noise that I've never seen before. There are ways to actually train just a complementary autoencoder that conforms to the latent space you've learned before. And what that means is we don't have to learn everything from scratch. Every time you see a new situation, you just add this new style into your system without having to change everything that happened before it. So just to give you a couple of examples, I kind of forget what they are. Let's see. This is an example of I think it's a noisy speech.
We stopped under the willows by Kenton Park and lunched. It is a pretty little spot there, a pleasant grass plateau running along by the water.
So not very challenging noise. And then this is what happens when we re-render that in this sort of clean speech style.
We stopped under the willows by Kenton Park and lunched. It is a pretty little spot there, a pleasant grass plateau running along.
So it mostly gets it right. Here's an example where we try to do the same thing with matching room acoustics. So here's the input sound that we have.
Although the breeze had now utterly ceased, we had made a great deal of way.
And then this is what we use as a reference style for style B, which is going to be a reverberant speech.
A little spot there, a pleasant grass plateau running along the water's edge.
And now what we do is we basically move the input to conform to the style of the second recording. So we get this.
Although the breeze had now utterly ceased, we had made a great deal of way.
So it kind of adds the right reverb. It has a kind of similar noise. So it gets the idea that we're trying to sort of transfer that style of a recording. So I know it doesn't completely answer your question, but that's an example where the reverb and the noise had to be hallucinated to match the other recording. Yeah?
How narrowly do you define style? Like, so now when you have reverberation, is it reverberations in this particular kind of room, or reverberations?
I think when we trained it, we just did room-specific data sets. I don't remember if we did multiple rooms at the same time. So I don't know is the quick answer.
Doing on noise, I mean, would you always have the same kind of noise
Yeah, for noise, it's actually easier because if you only want to do denoising and not necessarily add noise, the statistics of clean speech are fairly consistent. So that's an easy model to learn, and you can train it with multiple noises and have it rendered in the style of just clean speech. And I think we had a paper on WASPA maybe a couple of weeks ago on that. I think the difficult one is when you have what Sinji mentioned. Well, put some noise in there where it has to improvise. And in this case, again, it's a little simple because the noise was kind of stationary, so it was kind of obvious what to add. If you train it on police sirens or meowing cats, then it's going to be a different story. Okay, other questions? All right. Okay, so far what we have is that we can run things somewhat fast using the binary networks. We don't have to worry too much about collecting data that matches. So what's the next thing I want to talk about? Well, the next thing I want to talk about is that forget doing supervised learning altogether. Getting any kind of clean data, sometimes it's hard. It's very easy for me to get a lot of really noisy speech data. It's not easy for me to get clean data, right? It costs money and takes time. It's a big operation. And especially in the application case that we have, you're going to be walking around with those devices in your ears. You'll never get studio quality audio coming in. You're always going to get real life audio coming in. So how do we learn in the wild? So there's obviously the part of it which is just, let's try to solve this problem. I think there's also a very deep sort of science question to be answered here. I'm a big fan of the idea that as somebody who works on audio, what I really care about is how did hearing evolve? And I'm a big fan of sort of evolution sort of mirroring our environment. And the story I usually say is that, a couple of billion years ago, our ancestors did not have ears, but by being exposed to sound, they developed ears. So I want to do the same thing with computers. Hopefully it's going to be a little faster than that. But the idea is that just by listening at sound, you should be able to develop a sense of hearing. I shouldn't have to say that there are phonemes and frequencies and all these things. So it should be something that you just pick up. I'm not saying that you pick this up as a baby, but as a species, we did pick this up. And this is really unsupervised learning, right? I mean, this is what I care about as a scientist. This is what to me is the big question. So trying to sort of address both of those things at the same time, there's a couple of things we have to worry about. So one of them, for example, is how do we define a source? So far, the way that we define the source is we either had a clean target that said, this is what I want you to produce as an output, or these are the sounds that make up a mixture, or we had, or we basically had sounds that exemplified what it means to have a single source. Now what we're going to do is use a different option. Instead of me saying that this is a clean separate sounds, what we're going to use is we're going to start using spatial statistics to help us understand what constitutes different sounds. And the basic assumption here is that different sounds tend to come from different directions for most of the time. So on average, you should be able to understand what constitutes a different sound in a scene just by observing the spatial statistics. Again, this is something that's sort of well understood and accepted in the hearing literature. In fact, if you look at hearing, all animals but one have more than one ear. There's only one animal that has one ear, right? All other animals have two or more ears, and that's what helps us basically understand what's going on around us. Without that, you wouldn't be able to get a sense of it. And I'll leave it as a mystery what that one animal is. You can ask me afterwards. So what we're going to do here is the following. We're going to start getting some kind of statistics in the spatial domain. But again, the goal, remember, is to try to understand what constitutes a source. It's not necessarily to use a microphone array, right? So remember that because we're going to get back to it. So for now, we're going to use something that's well known. I'm going to use a set of features known as duet features. That was a very smart algorithm that came a few years ago. And the basic idea behind it is that, for example, you have two microphones. You're recording the same scene using these two microphones. What you can get is features that tell you something unique about where the sounds are coming from. And the idea behind it is that you would take your two spectrograms in the complex space from your two microphones, you would divide the two together, and then if you look at the amplitude of that ratio, that would effectively tell you how much louder is one bin, the same bin between the two across the two microphones. And then you can also get something equivalent to a time delay difference by looking at the phase offset between those two recordings. So by looking at the amplitudes and the time differences for every time frequency bin independently, what you effectively get these plots would look like this. So this is the same spectrogram as before, but now I replaced every time frequency bin with a log ratio between my two spectrograms, and this gives me the time difference. Now, if I were to take all of those points, if I take, for example, a particular time frequency bin and treat it as a two-dimensional variable where it has one element being the magnitude, the ratio, and the other one being the phase, if I were to plot them in a 2D space, they would look like this. And what does that plot tell me? It tells me that I have a lot of time frequency bins that have a similar time offset and a similar level difference between my two microphones. And likewise, I have another set which have a different behavior. So there's a sound coming from a location that has this particular level difference and phase differences, and another sound that comes from here. So this effectively tells me I have two locations, and this is where they are in that 2D space that I'm operating on. Now what I'm going to use is those features as a way to distinguish separate sounds. And the way I'm going to do it is I'm going to using a targets for a network. So the basic idea is that previously, when we try to learn such a network, we usually use some kind of a binary mask or some target output, which is going to be what we want. Now we're going to do something different. We're going to try to find a latent space to project our input spectrogram that's coming in, such that it has the same geometry as the spatial features that I found here. So that means that if I provide a spectrogram coming in, I want to find a way to project all of those time frequency bins in a 2D space that kind of looks like this. And if I do that, that means that I will know which time frequency bins belong to one source and which ones belong to the other one. And the way that I do that is I try to find an embedding that the network will give me that would basically look similar to an embedding that we have in this spatial feature space. So this is basically an extension of the deep clustering networks, which Sivji was a part of in developing. A very neat idea. The only difference is that I'm not going to use hard labels Y, which is what was used originally, where the user had to specify what parts of the spectrogram belong to one source or the other. Instead, I'm going to be using the soft features, which are going to be my spatial features. So at the end, what happens is that I get a network that can take a spectrogram, project it in a space where my time frequency bins are being represented as different clusters, and then I can do my clustering and pick whatever it is that I want. Now, here's the catch. What I've done here is that I've used a microphone array to get some spatial data, but then when I run the system, I'm not running it on multiple microphones. The way that it's going to run is that I'm going to get a single microphone input, and I'm going to use the knowledge that the network has accumulated by listening at stereo recordings to find a way to project all of these pixels in my spectrogram in a space that sort of separates the sources best. And then I can project back to the original space that I was in, and all the blue points will basically give me one spectrogram, and all the green points will give me another one. So what's neat here is that we use the spatial statistics to learn what it means to be a source, but then we're applying that on a single channel example. Right? So what that means is that, yes, you might have a species that evolves with two ears, but even people with one ear will be able to perform listening tasks because they're using that accumulated knowledge that's hardwired in the brain. You don't have to basically just stick to this multi-sensor input coming in. So what I find most exciting here is that this is a network that actually learns what a source is by getting this side information, but it doesn't necessarily rely on just the spatial statistics, which I think is kind of cool. But also for practical purposes, it means that we don't have to have labeled data anymore. It means that we can deploy systems. We actually have an array that sits out there, it's just listening, day in and day out, and its job is to understand what are different sounds. And it does that by taking taking note of the spatial statistics, but ultimately it's learning how to separate sounds from a single channel recording. All right, so to recap, so I talked a little bit about how we can run things fast and cheap by using binary networks. I talked a little bit about how we don't need to have matching input and output data if we treat a lot of audio problems as style transfer problems. And then part 3, I sort of made my pitch for unsupervised learning, which ultimately I think, this is the fun part if you do anything with machine learning. So going back to the big picture, again, our goal is to try to augment our listening environment. We need to have devices that understand sound in a very deep way. There's a lot of challenges. The stuff that I talked about was mostly on, how do you do this edge computing on those devices? How do you deal with getting data in a form that's usable in the problem you're working on? There's a lot of other stuff that I didn't talk about. How do you do, for example, federated sensing? If you have multiple people wearing those hearables, how can they collaborate being completely unsynchronized sort of array elements? Or how do you do an interface for this thing? How do you make a device where you can say, I like that sound, I don't like that sound, or make that sound better? These are very, very interesting sort of problems to work on. So I foresee a lot of my time getting there, so and there's no shortage of stuff to do. Finally, shout outs to my awesome students. So Minji Kim did most of the work on the binary networks. Shrikant Venkataramani did most of the work on the style transfer. And Phineas Genius did most of the work on the unsupervised learning. But of course, they're stepping on the shoulders of my previous students that did other work. So big thanks to them for doing all that work. And if you have questions or anything, feel free to contact me. I'll be here for questions too. And that's all for me. Thank you. If I recall correctly, we didn't use a lot of data. It was mostly in the order of seconds or minutes. So we were using the DAPS database, which isn't that big, but it just has lots of different acoustic conditions. And I think for small targeted problems, that can work well. For the bigger denoising problems, I think we actually used a bigger data set like Wall Street Journal and like sound effect CDs. So I think depending on the problem and what you're trying to do, I think the answer is going to be different. If you want to do something like denoising, you can use big data sets, and the bigger the better. If you want to do something like change style from room A to room B, you can get away with a much smaller data set because the difference will be exemplified much easier that way. Yeah.
On the factorization part,
Hmm?
do you have any characterization about how the depth of the network affects the error? Because I see properly the
Yeah. So we mostly focused on doing a one-to-one comparison with the real valued networks. If you use wider or more layers, the performance went up, but in not in a special different way as compared to the real networks. So there wasn't anything special to report there. It roughly followed the real network sort of behavior.
And when you do the fine-tuning stage that you mentioned,
Mm-hmm.
is that also just at the output, or like I can imagine for every layer also?
No, it's the whole network is optimized at the same time.
Any other questions?
How what? Yeah. Mm-hmm. Well, the goal was not to highlight that it generalizes better. The goal is to show that you can learn how to deal with a new situation in a more efficient way. So I think most of the experiments that we have demonstrate that, yes, you can pick up a new problem really fast, but I don't think we're necessarily claiming that we can generalize better. So there's a subtle difference there. Yeah. For so usually what we do is we have a whole bunch of audio effects CDs, like the BBC collection and all those things. Then we have a huge directory with a whole bunch of weird sounds, and then we say all of those things could be noises. So for artificial mixers, we just use those. For the style transfer, we use the DAPS dataset that has some built-in noise by itself. And then for like specific cases, we had like, here's somebody just talking over music or something, and that was we just had to custom make some sets for that. Yes, we only use real data. Well, the paper had had the synthetic data as a proof of concept, but we do have an array running in my office, and it actually collects real data, and it gets there. No. I'm not a big fan of voice conversion because there's a lot of high-level stuff you have to worry about, and it's not really a signals problem. So, if you magically start speaking with my accent, you will sound more like me than you sound like you, right? So it's not really an audio problem. It's really a sort of a parameters behind the voice. So I think one thing that makes me somewhat uncomfortable with style transfer is that it's often very ill-defined. There's a lot of people trying to do music style transfer, for example, but nobody knows exactly what it means. I think what I liked with our implementation is that it was very clear what the style is because it was a very constrained, very simple signal kind of operation that made the style transfer. Once you go into stuff that's called high-level parameters, I don't want to touch those things. It's much more difficult to work there. So I'm pretty sure that for voice transfer, this thing would fail spectacularly.
Okay, thank you.
Thank you.
What's the animal?
Huh?
What's the animal?
The animals, praying mantis.
Praying mantis.
It has a knee on its chest.
Figure, since I have to come up here to stop the recording anyway.